which will be presented by Jose Angel Miranda, who is a postdoc research assistant and scientist at EPFL. And he's going to present his topic on GenAI and the transformation of edge computing, leveraging heterogeneous circuits for innovation. Jose?
Thank you so much for the introduction. Yeah, as you said, I'm Jose Miranda, postdoc research assistant at Embedded Laboratory in EPFL. So my presentation is going to be a little bit more on the hardware point of view, and I just wanted to give you a brief outline of the presentation which I'm going to be providing, and I want to go, let's say, to tackle the current landscape, some of the challenges and progresses of, and also future directions on how the Gen AI is transforming the current edge computing, right? In order to reach its computational and, let's say, energy efficient usage into very constrained platforms and devices. Also, I will try to discuss specific bottlenecks on the edge devices on these very high constrained systems, and how, for example, specialized accelerators are helping to boost the possibility of having Gen AI into the edge. We will review some open source frameworks that are able to explore and generate different heterogeneous system on chips, providing rapid prototyping, and how we are currently overcoming those computational and energy constraints. And yeah, at the very end, we're just gonna be spotting some future directions. So actually, nowadays there are plenty and many different trends into the edge technological landscape, such as, for example, orchestrators between the edge and the cloud, privacy by design principles, incorporating specialized hardware with trusted execution environments, the well-known edge-to-edge collaboration by using or by leveraging the edge as a service. Also, we have a lot of different open source deployment optimization frameworks for on-device inference and training, such as, for example, one of them is training engine. But actually, the trend that is, let's say, the biggest one, or at least from a point of view, is the integration of Gen AI into the edge. So this integration is not just about making the models smaller, more secure or more optimal, let's say, in terms of edge to cloud data transfer and synchronization, but also about coming up with new deeply heterogeneous processor architectures that are actually, let's say, tackling different computational bottlenecks that we are currently having. And so just in order to put some numbers over the table, for example, putting in Gen AI and edge computing together, as I said, it's not about technology. It's not just about technology. So, for instance, the annual global AI data center cost cloud, based on Tirias research estimations, top to $66 billion by 2028. This is just an estimation, but let's imagine that we are able to offload just 20% of the computation to be done on the cloud to the edge. That will result into basically a decline by 15 billion. This will also include a considerable saving on carbon footprint. For instance, by reducing the power requirements by, for example, 800 megawatts. Note that this is like saying, for example, that we are saving, for example, something like 2.5 million metric tons of coal, or several million solar panels. This matter has been even addressed already this year in the World Economic Forum, where they also stated the need for boosting this integration of Gen AI into the edge. However, they also identify different, let's say, needs regarding this evolution of on-device AI. And they say that this on-device AI necessitates or needs some advancements in hardware capabilities, energy efficiency, and also, of course, the algorithm optimization part. So let's say that bridging these gaps could democratize AI, making technology accessible in regions, for example, with limited connectivity. However, the problem also regarding, for example, if we are looking at where this type of computational workload should be running, the problem is that even with the potential for on-device processing, many models, and we have seen it, we are seeing it day by day will exceed the processing capabilities from device processing, and or, for example, will require cloud interaction, right, for a different variety of reasons. In fact, for example, the performance of the performance improvements in let's say mobile SoCs or constrained edge devices will not outpace the parameter growth of some GenAI applications, like for example ChatGPT. In this sense, one possibility or one solution could be some type of hybrid GenAI processing, when some parts are executed on the device and other parts, heavier parts, are executed in the cloud. So even though we could be facing these, let's say, hybrid computing approaches, we still need to consider a heavy workload being executed or being run at the constraint edge. Based on this, for example, there has been different funding programs already targeting at the next generation of AI chips. For instance, for example, this is also a well-known funding program. This is called Optima, with the goal of to achieve these 300 tops per watt, or in other, let's say, words, 20 tops per millimeter square. And so in this specific funding program, for example, just to mention the two technical challenges, they said that these two main challenges to be achieved were basically achieving a small and power efficient multiply compute element and achieving a small, scalable and power efficient multiply compute storage. So uh, uh, the main message in here is that we already know what is the bottleneck, and the bottleneck is related to memory. So it is actually much more expensive, the memory accesses, than the computations. And in this manner, based on this context, there are two main blocks to be explored towards this new and more heterogeneous brain-inspired edge architectures targeting such tops per watt. First, we have the domain-specific accelerators. So just to give let's say, a contextual point of view, from an application point of view, they're different with respect to, for example, common CPUs or even GPUs is clear. They are more constrained by design, or, for example, focus on specific domains or applications, but at the same time, they can reach better performance metrics per watt. That is, they are tailored to meet the needs of the algorithms required for that domain. For example, for, let's say, audio processing, a processor might have a set of specific instructions to optimally implement, for example, different algorithms for echo canceling, keyword spotting, and so on. In another example, for example, an AI accelerator might have an array of elements, including multiply accumulate functionality, in order to energy efficiently undertake, for example, matrix multiplications, right? In this context of domain-specific accelerator, DSAs, we have already, let's say, some powerful or potential candidates. For instance, for example, one of them is when targeting transformers. When targeting transformers, for example, we're targeting BERT. Here we have one publication from 2022 coming from NVIDIA. And so basically this is, just to put it also in context, this is one of the best domain-specific accelerators targeting transformers, and they are reaching something like 95.6 TOS per watt with 1,711 inference per second per watt. They are implementing per vector scale 4-bit quantization in a 5 nanometers technology with only a drop-on accuracy of 0.7%, which is basically, so they are achieving these numbers basically due to their specific hardware accelerator that they have designed for this specific use case. There are other examples. For example, let's say that coming also from the more research point of view, we have also a very high performance and energy efficient solution integrating, let's say, heterogeneous flavors of different domain-specific accelerators. In this case, we have Kraken, which is another ASIC done by Pulp from ETH, and they are, besides having a cluster of different RISC-V CPUs, they are having actually two different domain-specific accelerators, one for spiking neural network and the other, which is called Qt, which is actually a ternary neural network. So again, trying to go to the minimal number of bits as possible. And this is the paper. So as far as I know, this is the paper. This is the first paper that is actually breaking the limit of the peta operations per second and per watt. And so then the other, let's say, block that will enable, or that is enabling these next generation AI chips is in-memory computing. In this case, let's say that if we remember that it is more expensive, the memory access, than the computations, what happens actually is that the memory computing tries to perform computations directly in memory. In such a field, there are digital, for example, and analog implementations. Nowadays, for example, this is a specific company, Encharge AI, and they are the ones that are providing one of the best solutions for in-memory computing in the analog domain by considering a very specific technology for the, let's say, specific solution by considering standard CMOS capacitors. And at the end, they are reaching metrics that are basically up to 150 TOPS per watt. So again, very good metrics implementing this type of technologies, this type of heterogeneous blocks within different system on chips. So, but however, what is happening is that heterogeneity and complexity is limited just by designer's time. I mean, designing a system on chip, a ASIC, that is having all these different domain-specific accelerators and or in-memory computing blocks and so on, I mean, it's time-consuming. So you don't have actually the time to test everything in every single bit precision combination, or, for example, with different type of buses and so on. This is why, for example, lately there is a emerging topic that is intending to tackle this issue, and these are called the open source frameworks for ASIC generation. So in a nutshell, these are rapid prototyping ASIC enablers with many different flavors and optimization steps that allow you to easily evaluate different system-on-chip architectures, or in other words, to easily integrate and interface ad hoc hardware accelerator. So the one that you are doing to actually interface it with a, let's say, system-level SoC. In our case, at the Embedded System Laboratory in EPFL, we are developing the platform that is called SHIP, which allows you to actually do this rapid prototyping and to lastly couple, for example, different accelerators or coprocessors to a configurable and highly modular and extensible SoC. There are other alternatives and approaches, such as, for example, ESP from Columbia University, or on the private sector, there are also solutions such as Dolphin, for example, such as Chameleon from Dolphin Design. So just to give specific examples on this, by using this type of rapid prototyping frameworks for these new heterogeneous SoCs, we can easily evaluate different solutions trying to overcome these computational energy constraints. For instance, for example, we can produce different versions of these system on chips, some of them with loosely coupled hardware accelerators, such as in this example, we are having a CGRA, a coarse grain reconfigurable accelerator, and we can evaluate the trade-offs before even going to the tape out. So before even producing these ASICs, and once we have verified that, okay, yes, I got the acceleration that I want, then we can go easily and with less time invested into, for example, the tape out. This is, by the way, this is Hippocrates. This is the last tape out that we produce using SHIP, the platform that I told you, with adding different, let's say, heterogeneous flavors, such as, for example, in here we are in this specific CRA hardware accelerator. In the same way, when dealing with in-memory computing, for example, in our lab, we have developed different in-memory computing techniques. One of them is called Blade. This is a new in-memory computing developed at our lab, and basically it's a SRAM SRAM computing architecture that basically leverages the local word line groups to actually do different computations at a frequency that is much higher than the state of the art in this specific in SRAM computing architectures. And in the same way, we can actually do different testings and different evaluations before even going to the AC production, and then later on we can go to this tape out in order to have a deeply real heterogeneous SoCs having both domain-specific accelerators and in-memory computing blocks. So what are the future directions? Once we have this type of platforms that are able to easily and rapidly evaluate different SoC, let's say, architectures and these deeply heterogeneous processors. So the future is that we need basically to generate an end-to-end hardware-aware deployment platform or framework for these specific processors and for SoC architectures by having an end-to-end framework. And I mean end-to-end, starting from the application, applying, for example, different types of quantization, such as quantization aware scaling or whatever quantization that we can think of, and also tackling and also linking this to the SoC.
Thank you very much, Jose. So we have right now we have one question, and we have actually time for 2 more minutes for question and answer. So one of the questions is basically, in your talk, were you trying to infer that you're reinventing ASICs with your domain-specific accelerators? So it's a little general question.
What?
Reinventing ASICs with your domain-specific accelerators.
No. We are not reinventing ASICs. So actually, what we are doing is we are using. So SHIP is not reinventing anything. We are taking open source silicon proven IPs, and we are using those in order to generate novel architectures. We are not reinventing anything. We are taking everything open source, and in fact, SHIP is open source. You can check it out. This is the main point. We are giving the power to the people to actually create their own stuff by using stuff that is already there and that is silicon proven.
Oh, okay. Another question came. What is your view of analog versus digital IMC?
Analog versus digital IMC. Okay, so yeah, that is a good question. And that is a tough one because there you have different profiles of people. So, I mean, it depends on the application actually, and it depends on the architecture of your system. But at the end, I mean, there are advantages and there are disadvantages. I don't want to put one over the other because there are different types of, let's say, perks to take and to consider. But at the end, the good thing is that you can have both implemented, and you can actually use, as I said, these type of platforms like such as SHIP in order to have a rapid evaluation, rapid testing on what is the actual trade-off of having one or having the other.
Thank you. So 2 more questions. Possible to tape out soon? Are you taping out soon?
Possible to?
Tape out. Building
yes,
the...
Yes. We have actually this is the layout that I'm showing in this slide. This is actually Hippocrates, and this is a real tape out that we just did, and it is working. And and this is based on a very specific SHIP configuration. Again, not reinventing the wheel. This is super important. So we are just taking open source silicon proven IPs coming from different parties such as Pulp, Open Titan, Open Hardware, and so on. And what we are doing is that we are putting our, let's say, domain-specific accelerators or our in-memory computing blocks in a rapid manner. So we want to explore, we want to do rapid prototyping. So yes, this is totally, let's say, silicon proven, and you can go for a tape out, yes.
All right, so I think we should move to the next question. There was one more question, Jose, if you could answer, actually 1 or 2 more questions, maybe on chat. And I'm really glad that there is this active participation by the attendants, that they're asking questions. And this is really, I'm encouraging everyone to keep continuing that. So thank you, Jose.
A big thank you again to all of our sponsors that make this possible. In particular, thank you to the executive strategic partners of TinyML, Qualcomm AI, advancing AI research to make efficient AI ubiquitous. Also Sentient, making edge AI a reality. The platinum strategic partners, EmbeddUR, Sony AI to deploy vision AI at the edge at scale. The gold strategic partners, ARM, Edge Impulse, Infineon, Renesas, ST Micro, and Synaptics. And the silver strategic partners, which we have here, AIZip, Arduino, BrainChip, Bfission, Greenwaves, Gravity, Hymax, Imagimob, Initera, Noda AI, NXP, Procter & Gamble, Schneider Electric, SensiML, Silicon Labs, and TDK. So that concludes our first day. Don't forget, we have a lot more action-packed agenda for tomorrow as well, starting at the same time. So that concludes our session for today. And thank you for joining, everyone. See you tomorrow.